in the last class, we discussed about this. Particles are classified like matter, matter that can be classified as electrons. Then we have that exchange particles. Then so in this electrons, we have electron, proton, electron, and the particle of this and the particles corresponding to mass. Then we have these exchange particles consist of photons, photons, is comprised by okay, so in this case we are considering ions here. And this one we will discuss in the third section. And we have hadrons. In these hadrons we have mesons as well as baryons. Already told mesons are the cork handy part there. The cork handy part. Baryons have full corks. This meson consists of high mesons or ions, A mesons, beta, and their antibody. So the pi mesons will be having pi plus, so that pi plus 0. Then beta and this set their antibody. Now, last one is baryons. Baryons will be again classified into this one is nucleons. So nothing but neutron and proton and their antibody. So we have CP and this is the cyclones consist of this sigma and cascade. Then we have omega, and we can have all these particles in hadrons and their antibodies. If you consider that this set of particles, if any interactions happens between these that those interaction will follow some conservation laws. First one, conservation of energy. Then we have conservation of charge. Then we have conservation of momentum. Conservation of baryon number. Number. Conservation of yes. So all these conservation laws should be satisfied in any interactions. These particles are interacting with each other and forming some new particles. So if you consider conservation of energy, some more conservation laws here. We will discuss some of this lecture. So conservation of strangeness, spin and its circumvent. So all these conservations, this conservation laws valid in all those areas. So we will be discussing some of the conservation. This energy conservation we already know. So if some reactions happens, for example, this Y Z is going to some Z and some X. Okay. So in this particular reaction, whatever energy we are having this side will be this side. And whatever mass in this side, whatever mass or energy you can consider. So the total energy of the reaction, the observed energy of this reactants. So that's about conservation of energy. So you have to know that conservation actions. When we have conservation of charge, this X is having some plus Q charge. This Y is having some N plus Q charge, and the resultant charge is total is 2Q. So this 2Q should be there in the products. So the charge should be considered in the reaction, but before what is that charge? Similarly, if we consider the conservation of momentum, so the momentum of these particles, suppose this axis and then in this direction, this can be this direction. So when they interact, their momentum should be conserved so that Z should form, Z and beta should form in such a way that the conservation of momentum is satisfied. So that the momentum before collision, before interaction, and momentum after induction should be cancel each other. So the net momentum should be before and after. And that's about conservation of and conservation of baryon number, conservation of these are the new words that we will discuss in detail. And then conservation of baryon number, conservation of and conservation of strangeness, conservation of phase spin, and so on. So these are the important laws in particles. So let's consider an example here. So let's consider mu minus mu1, which is decaying into one electron plus plus one. So in this case, you have to consider lepton number, for example. If you consider lepton numbers, so lepton number means if any particle which is coming in that lepton family, that will be having lepton number 1. If any antiparticle which is coming in, the lepton number means any particle in lepton family will have lepton number L equal to 1. Any antiparticle in lepton family will have L equal to minus 1. So in this particular reaction, if we consider lepton number, so leptons you can see from here, it's your electron 1 to 1 and electron neutrino, and they are antiparticles. So this set of particles will have lepton number L equal to 1. This set of particles will have lepton number, and all other particles will have lepton number. All other particles are not in one group, L equal to 0. So considering here lepton number mu minus, that is electron is in that lepton family. So this will be having lepton number equal to 1. And electron, this is also in that family. So this will be equal to this is also 1 because an electron neutrino, antiparticle of electron. So this will be having minus 1 because it is antiparticle of electron neutrino. Then again mu neutrino, which is plus 1. It's not so the total L equal to 1 here. This side also is 1. So both sides vector number equal to here it is 1, here is also 1. Both sides the vector number is 1. So electron number is conserved. Now if you consider electron number, in that case we consider electron number. So for muon electron number is 0 because it is muon. Now electron we have electron number is equal to 1 and plus the anti-electron that is minus 1. Okay. So muon which is having it is not electron or electron neutrino, so that is electron number which is equal. So this side we have 0, this side also 1 plus 1 is 1, it is 0. So this is also right. Now if you consider muon electron number conservation, so, yeah, that will give for muon this is equal to that will be equal to electron for electron it is 0, for electron neutrino also it is 0. Then we have electron muon, this is plus 1. So this is also right. So in this reaction, all electron number conservation valid. Only electrons are present, so this reaction is possible. Allowed. Now we will consider another example for baryon. Before we go to the baryon, we will talk about something isospin, something about isospin. Okay. So isospin is a quantity which we use to distinguish the baryons. When you consider that distinguish all those particles. Okay? So if you consider that neutron and proton, or if you consider proton itself, so if you consider neutron and proton, if they interact each other under their force, When there is a nuclear force, the nuclear force is charge independent. It will treat neutron equal to they will be said when we are considering the force. The is charge independent. So in its view, so we have for nuclear force, both neutron and proton are same particle because there is no charge difference because nuclear force is charged. Okay, so for considering nuclear force, neutron and proton are same. So in order to distinguish these particles, we introduce another term which is called as isospin of the particles, and this isospin can be calculated by using equation m equal to 2 pi plus 1, where m is the multiplicity, I. Now let's discuss about this multiplicity first. So multiplicity means if you consider that barium group, so this barium is nucleon, and then we have that electrons for electrons. So the nucleons have neutron and proton. Electrons we have different classes. So plus plus minus gamma plus gamma. See, I put this nucleons So these nucleons consist of total number of particles in this nucleon group is 2. So this total number of particles is which is called as multiplicity. So in this case, the multiplicity is nothing but 2, and we call this as doublet. Okay. So in this case, if you consider there are 3 particles in this group, so this is a triplet. So multiplicity m equal to 3, and which is called as triplet. And if you have a different m value, that is, if you consider omega, then it is singlet. So, so that is the multiplicity, how many number of particles are there, and that will give you that multiplicity. Now, if you consider this case, then your multiplicity m equal to 2, which means that 2 equal to 2i plus 1. So I will be equal to. So for neutron and proton, your isospin is 1 by 2. Okay. Now, which one will have? Okay, I will discuss here also. Then. So in this particular case, sigma, we have m equal to 3. Okay, so that means 3 equal to 3 equal to 2i plus 1. That will give me I equal to 1. Now there are 3 different particles. So which one will have plus 1, 0, yeah, plus 1, 0, and minus 1? That we have to consider. So we have the isospin corresponds to this particular particle, which is 1 to I. This one, so this one. So which one will be having those values? So we have to calculate that before this isospin can be also calculated from I equal to Q minus Q bar. This equation. So this Q is the charge of particle and Q bar is the average charge of the group. So let's say that here, so I will be equal to, in this case, I'm talking about this one group. So Q will be equal to, Q is nothing but the charge of the present particle. Q bar is the average charge of that group. So Q bar will be equal to, proton is having charge plus 1, neutron is chargeless. So total number of charges are, total number of particles are 2. And total charge is 1. So 1 by 2 is the average charge. So this is the multiplicity of number of particles in that group, and in the numerator is the total charge. Of so Q bar will be 1 by 2 in this particular case, and if you consider it for proton, that will give Q equal to 1. Therefore, I will be equal to 1 by 2. Sorry, I will be equal to 1, 2 minus Q bar. 1 minus Q bar is 1. So that will give me plus. And if you consider that for neutron, that will give Q equal to 0, the charge of neutron, which is equal to 0. So therefore, I will be equal to this Q, that is 0, minus 1 by 2 is the average charge of Q. So this will be. So which one is having highest charge will be first. Let's consider this to this equation Q is Q bar. So I equal to Q is Q bar for sigma minus, sorry, sigma plus first. For sigma plus, Q will be equal to plus 1. So I will be equal to 1 minus, what is that average charge for this group? Average charge Q bar equal to plus 1 here for sigma plus, then 0, then minus, the average charge is 0. Total charge is 0. Total charge is 0 divided by total number of particles. Okay. So you have Q bar, which is equal to 0. And for sigma plus, Q is equal to plus 1. So 1 minus Q bar is 0. This is having. If you consider G sigma 0, then Q will be having 0, because charge of sigma 0 is 0. This is that charge. Then I equal to 0 minus 0. And for sigma minus, equal to minus 1, I will be equal to minus 1 minus 0. So from here we have I equal to 1 from this equation. So this I equal to 1 will be split like plus 1 to minus 1. So plus 1 will be taken by the highest charged particle, and the last one minus 1 will be least charged particle. So this will give you plus 1 plus 1. This will be taken by sigma plus 0. Now if you consider this group, then you have multiplicity m equal to 4. Okay, so 4 equal to 2i plus 1. So I will be equal to 3, which means that plus 3 by 2 minus 1 by 2 and and this will be taken by delta plus plus delta plus. You can also use the other equation I equal to 2 minus bar. So here Q will be the Q bar for this group. Q bar will be equal to average charge will become 6 plus 3 and here 1 minus 1. So average charge is 2. So 2 by total number of particles 4. So and so this is Q minus 1 by 2. We take delta plus plus and Q will be equal to 2 plus 2 charge, 2 plus charges are there. So Q equal to 2. So I will be equal to 2 minus 1. So average charge here is 1 by 2. Okay, okay, right. So this will become 2, 4, okay, 3 by 2. Okay. Now if you consider delta plus U equal to plus 1, and that will be I equal to 0, equal to 2, equal to 2, and delta minus U equal to minus 1. So I will be equal to plus 1 minus 1. So this is how we will calculate the isospin corresponds to different particles. Okay? And this isospin also has to be conserved in all those reactions. Okay, now we will check example for baryons. There is one more equation. I will just show that. If you want to calculate the charge, Q by E will be I3. I3 is Z component of that isospin. We will discuss about that later. So it's plus P by 2, where S is the strangeness, B is baryon number, and I3 is the Z component of isospin, as we discussed in the LZ and L. Similarly, here we have I and I3. So I3 is the Z component of that I. Okay, we will consider the baryon conservation now. Example for baryon number conservation. Okay, let's consider the reaction neutron from P plus. So this is proton, so charge is plus, and electron, charge is minus. So consider first we consider that charge conservation. So charge conservation for neutron we have charge which is 0. So that should be equal to this should be equal to proton charge is plus 1 plus electron charge is minus 1, which is conserved, plus this is 0. So both, in this reaction both end have 0. So before and after it is 0, charge is 0. In this reaction we say charge is conserved. Okay. Then we look for electron number conservation for the case of electron number. So electron number conservation we do not yeah, here we have n, which is neutron, which is a baryon. So electron number is 0. Then we have proton here. This is also not electron, so it is also 0. But when you consider the last one, electron is electron, right? Which is in that electron group. So this will be having 1. So electron number is not considered because electron numbers are not equal before and after. Next, we consider, so this reaction is not possible anyway, but we will consider the baryon number conservation also. So you can write about this baryon number conservation like the baryon number conservation. In baryon number conservation, we have baryon number equal to 1 for all baryons, all the particles which are in the group of baryons. Then baryon number equal to -1 for all particles, antiparticles, for all antiparticles in the baryon group. And for all other particles, baryon number will be equal to 0. Similar to that electron number what we have. So in baryon number conservation, we have n here, so that is a baryon, so it is 1. And proton, which is also a baryon, which is particle, not antiparticle. So this is also 1. And then electron, which is not a baryon, so it is 0. So 1 equal to 1. And then the last case we have to consider we can consider strangeness. We will discuss it later. Yeah. So these three conservation laws, if we consider, they are conserved. So the electron number is not conserved, or others are conserved. So any of these conservation laws violating means that that reaction is not possible or it is forbidden. So this particular reaction is forbidden. Is forbidden. So, okay. That's why we consider when you have that beta decay process. So when neutron becomes proton plus an electron, we need some antineutrons. In this case, if you consider that electron number conservation, okay, electron number conservation, this is 0. Then we have proton, this is also 0 for proton. And then plus and neutron we have +1, antineutrino we have -1. Okay? So because this is antiparticle, so we have -1 here. So the total of this will become 0. So here also we have 0. So now this is conserved, or electron number is conserved. So this reaction is possible. All other these are conserved, charge and baryon. now this reaction is. So you have to check all those conservation laws, the momentum conservation, the isospin conservation, the iron number conservation, electron number, all those things. Any of them violating means that is not those back reactions. If all these conservation complete, then the reaction is allowed. Okay. Now, if you consider any other case, other reactions, also we have to look into like those reactions like this. We have to put all those conservation laws and check any of those conservation rating, then it is not going to conserve any reaction. Okay. Now let's consider another example. Let's say pi minus, one more example. We'll discuss much more about the isospin conservation, strangeness conservation. So, yeah. So let's consider another example, pi minus, which is decaying into mu minus and antineutrino. So from this, these neutrinos are not having any charge. So the charge is conserved here because by looking itself, you can see this is -1. That is equal to -1 here plus 0. So charge is conserved. Okay. Now if you consider baryon number conservation, so baryon number is for pions, they are not baryons. So they are baryons. They are baryons because it is mesons family. So 5 mesons. So these are baryons. So this is 1, which is equal to mu. Muons are not baryons. So this is also it's not allowed. I think so. This is that mesons, hadrons are classified into mesons, right? These are so pions are also not baryons. Be careful about that table. Otherwise, you cannot do this kind of calculations. So this is 0 baryons because the pions are mesons. So this is hadrons which are classified into mesons and baryons. Then these baryons are classified into further metals and like so mesons are not baryons. So this is 0, 0, 0. So this is okay. This is also conserved. And then we have to check lepton number. So if we consider lepton number, we have to check mu lepton because only mu leptons are there. So for pi it is 0 because it is meson, and this is 1, right? And mu neutrino, this is antiparticle, so this is -1. So this is also conserved. So charge, baryon number, and lepton number are conserved in this reaction. Now we have to check that strangeness and isospin, all those things that we will do in the next class after discussing about all those things. Before that, we will do one more problem to check the conservation. So consider a case. I don't know whether We can check another one. I'll check mu E. Check whether this reaction is allowed or not. The reaction is mu E going to become plus 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 one proton will give you one plus I plus plus. So whether this reaction is valid or not, that we can check. So in this particular case, if you consider, we are now checking only this charge baryon number and conservation. So consider that charge first. The charge here it is 0, here it is plus 1. Then we have electron which is minus 1 charge plus 5 plus is plus 1. And again plus 1 for proton. So total plus 1 here, minus and plus 1 and plus 1 here. Now we consider baryon number conservation B. The baryon number mu E is not a baryon. Proton P is the baryon. So this is one. That will give me electron which is so this is electron which is not a baryon. Ion, not a baryon. So then P we have a so this is conserved. And if we consider that electron number conservation, we have only electron here, so we have to consider electron. So this is 1 plus 0, which is equal to electron 1. 5 plus this ion is on, so this is now we'll discuss one more. Let's consider a reaction. E and plus proton will give me mu minus plus consider first charge the charge for mu this is 0 plus charge plus 1 and that is equal to mu minus charge is minus 1 plus neutron charge is 0, so this is not okay. I will change this mu plus plus so that is antiparticle of mu minus, okay, plus then it is to this reaction side next it is plus is valid now. And if you consider that baryon number conservation here, baryon number will be over here plus 1 here is equal to mu electrons, so it is 0, n which is a baryon, so this one is valid. And if you consider electron number conservation, so this is L mu, this is 1 plus 0, this is equal to this one is 1. Now consider another interaction. Proton is converting into a plus electron plus antineutrino. So that we already So a proton which is converted into neutron plus electron plus antineutron. So we'll check whether this is possible. So first consider that charge. The charge is plus 1 here. 0 plus minus 1 plus 0. So this is not valid. This plus 1, 0, minus 1, that is valid. And if you consider baryon number conservation, that will give plus 1 here, plus 1 here, 0, plus 0. Okay. Vector number conservation, if you consider this is 0, 0, plus 1, plus 1. So this is not valid. So this reaction is not allowed. This is a proton converted into neutron plus electron plus. Okay. So if you consider the same reaction like proton converted into neutron plus electron plus this. Okay. So now this is positive beta decay. And in this case, what will happen? If you consider that charge again. So I just replaced this electron with positron. The charge will be plus 1 here, will be equal to 0. Charge will be here, plus 1. Okay, plus 0. So this is valid now. Now if we consider baryon number conservation, it's plus 1 equal to, here it is also plus 1. Yes. It's also conserved. And then electron number conservation, proton which is 0 equal to neutron which is having electron number 0, then plus positron which is having electron number minus 1, and electron will be having electron number 1. So if we consider this is 0, this total is also 0, so this is considered. Now this reaction is possible. This is not possible. This one is not possible. This is possible. So this is nothing but a positive beta. So this is okay. This is possible. So this is how we will check whether the reaction is allowed or not. Particle interaction is allowed or not. And we will discuss about the strangeness spin, isospin conservation, strangeness conservation, and the Z component of isospin. Okay, all those things. And we will also classify these reactions into weak reactions, strong reactions. That we will do in